just to recap, just to recap, the water and polymers are injected to pressure maintain to maintain the reservoir pressures, so that the oil the pressure is above the bubble point pressure for it to flow in single phase, which is the maximum permeability that we can have, and for pushing the oil out. So these fluids are injected for that purpose, as we know as petroleum engineers. Okay. So just to show you the figure, the deposition, how it looks like, as you can see at the bottom, this is how the particles do invade from the water or polymer solution, and they would, go into, and they may go deeper. I'll show you the model for the estimate of how far they can go, but I won't go into too detail. But basically, we have the model of how far things can go and how much porosity and permeability can reduce. Now, as this cake builds up over time, then we will having pressures too high, and then they may go above the breakdown or propagation pressure for the fractures to grow, and that alleviates the injectivity loss, but then they can get too long as well. So we need to model this phenomena. Okay, just to give you a little idea of how much solids we inject, the average, just the order is about a ton of solids every year that we would be injecting in a typical injection well or water injection well. Just an idea I'm giving it. It's not an exact for every well, but so for 5,000 barrels a day, if I'm injecting that, this is the number that you would have. So that's a lot of solids. So whether they would go deeper, whether they would filter out and develop a cake, that needs to be known. Okay, I'll show you some experimental results that will prove that, okay, we do have fractures, propagation, and we do have particles depositing inside. And so, a large piece of rock was, tested with injection water, which are typical quality, and under in situ conditions, where the minimum, maximum stress and vertical stresses are there. And they found that, okay, yes, there are fractures are getting caused, and the particles are around as orange colors, as you can see, around the fracture. So that proves that, yes, the particles do go inside the formation and fractures initiate. And they also measure the fracture length from their experimental results, and the propagation, can be seen here over 22 hours of test of the injection. So this proves that, yes, fractures are there and they do develop. This is the core after the test was completed. It was broken down, and we can see the big fracture face propagating as a circular shape going outward, and we can't see clearly, but the face, the mixtures of different particles that were injected, like silica, oil, acrylic particles, these are there, and rust particles were also being injected. Okay, so now the question is, yes, we have proven, we know this happens, this phenomena. So how do we model, and are there models already available? Well, people have been working, models are there, but like, for example, reservoir simulators typically have challenges to model this phenomena, which because of the small size requirement for the numerical simulation, for the grid size, because the deposition of particles are very close by to the wellbore or to the fracture. So the grids that typically are used in a simulator are very big, 10 hundreds of feet, because they have to model the entire reservoir. So that is one problem which they can do, but then the other main problem is the dynamic grids that they would require to model a growing fracture over time. So that would require the update of the grids and their permeability and their, whatever way they can model, and that's the challenge they have been facing. So I had talked to them, and they have been working on it, the CMG, for example, and I'm sure they must have reached to some point, but that's, they have their own challenges. So let's get started on the model here first. So the main model that I will show you, the two models that we're going to have is the near wellbore phenomena, near wellbore and fracture phenomena. How much is the pressure drop, and far away into the reservoir pressure drop, and then how much is the propagation pressure at the tip of the fracture. So these things I want to be able to model. The first thing is the particles, how far they go. So I start with the particle continuity equation, and this is the differential form of the equation. Basically, the flux is on the left-hand side, which is how much particle is coming out. That's the divergence. So basically, how many particles are coming out from a point, and then what is at that point, how many particles rate is changing. So the sum of the two should be 0 because there is no source term for the particles. So that's the differential form of the equation. I would not go into detail. The right hand side is the particles which are basically suspended and deposited. Initially, there is no deposition of particles when we begin. And so the idea is we are injecting some concentration of particles, and we want to find out how far they can go and what is the deposition rate, how much porosity gets reduced over time as particles deposit. So that's what we want to model. So for that, I make some approximations to the equation first. I neglect dispersion. And then the deposition, I can say that, if it is, it's proportional to the concentration, the rate is proportional to the concentration at a given point. The higher the concentration of particles, the more the rate is. But I don't know the coefficient of filtration, means that what exactly is the rate. So for that, either I have to do a filtration experiment, or I can develop again theoretical models which we have used done by other people. So putting this deposition rate formula inside the differential equation for the concentration profile that I want to find, and then only the C is the variable concentration, and this comes out to be a first order PDE, which can be solved with the boundary condition of injection concentration, which is at the wellbore at the core inlet. If you put this boundary condition, this differential equation, your beautiful solution comes out, a simple solution comes out, which is steady state solution, which is exponential in form. Basically, it says that concentration at the well is whatever you put in, and then exponentially it would decline depending on the filtration coefficient. So this is independent of time, and so whatever particle comes in, it gets deposited, and it maintains the profile. So we have two questions still remaining. What is the filtration coefficient and what is the rate? So we use the rate solution equation, and we can find the deposition amount and the amount of particles. The sigma is the amount of particles that are depositing, and whatever volume we get, we subtract from the porosity initial to get the final porosity. And we can see there the porosity is reducing over time. So this is the first is 30 hours. We got 0.19 from 0.2, and then it keeps decreasing and reaches to 0.16 at 90 hours. And it will continue to decrease until we reach some critical porosity of the cake, for example, 0.05 or something, and then no more particles would go in. And then we can start to develop an external filter cake. I would not show you those equations more further, but I got to give you the idea that this is how we transition from the internal cake to the external cake. This is one way of solving the problem. So, but the question of filtration coefficient is a tough one, because that is what is going to tell me, what is the profile and how fast the particles are depositing. Now that depends on a lot of factors, but basically I would not go into the depth. This is a model which is given by Rajagopal and Thian, which they use the Happel sphere and cell to represent the porous medium. And in this porous medium sphere, they have the flow field solved, and particle trajectory is calculated based on all the forces on the particles, and gravitational force, the diffusion, and and so these from the trajectory, they calculated limiting trajectory. They got the efficiency of the collector, and so we can perform these simulations, but then the benefit is that instead of doing the simulations to get filtration coefficient every time, they developed a correlation for all the simulations for different size particles, or ratios of particles, different buoyancy effect of density particle and fluid density, difference in that, how much the gravitational effect will be there, what the diffusion will do. So all these effects being clubbed into one equation, so we can just use a closed form of equation into our model instead of doing this simulation separately. So once we I did compare it to a lot of experiments, done over 80 years by different researchers, and found it's a reasonable model. And so we can use, so basically I use this filtration coefficient model. And so once we get the porosity updated near well bore or near fracture, wherever we want it to be, we want to find, we still have to find out the pressure drop. And so for that, I need the permeability updation. And so for permeability, I use Carmen-Cozzini equation. And the Carmen-Cozzini, we can get, we know it's derived by comparing flow, flow pressure drop in pipes and comparing with flow in porous media, which is Darcy's law. And we get this Carmen-Cozzini, and based on this model, we can get the permeability ratio, change in the permeability over time due to change in the porosity, a reduction in porosity and increase in specific surface area. And so these are not anyway the best models, but these do give us an idea and captures the effect. So after doing all that, I get the permeability in different zones. I calculate the pressure drop, so I can get the additional skin pressure drop near the formation, and from that I can get the increased bottom hole pressure, whether it's linear core flood or a radial well or a fractured linear flow, whichever situation it is. Once I do all that, I still need the, this is around the fracture. So these are just showing you some equations. You don't have to think, but basically I need to get the flow of particles around the fracture as well. And then the pressure drop around the fracture due to these particles, I get this total pressure drop, like a skin pressure drop around the fracture. And inside the cake, and also accounts for the cake. And also I can get the width of the fracture from PKN, kind of elliptical fracture, and I can calculate the, based on the leak off, I can get the initial weight and add the cake to it to get the final weight and the pressure drop along the fracture also, because I need to add the skin plus the fracture pressure drop also, because this is not an infinitely conductive fracture. It will have its own particles inside, and so that pressure drop has to be accounted for. So all that is near well bore. So we got all the pressure drop near well bore, near the fracture. So we got this additional pressure drop near the well bore. But what about the pressure drop in the reservoir? We can, that is more or less constant, but we still have to calculate it, because it may sometimes have an impact for the injectivity. For example, if mobility is changing, for example, if transient effects are there. So all this we have to still calculate, and for that what we do is we assume a single well injection, single injection well inside a reservoir, which is have a pressure known average reservoir pressure around this somewhere at some distance, and that is representing, we can solve the problem then, because this boundary is representing an average pressure, some average pressure, and we can calculate the pressure drop in these zones using Darcy's law if it's steady state. And I would skip a bit of slides now and go quick. One more thing is interesting is that I do want to mention is that to bring into your attention would be that when we inject water or polymer, we make these fluids at the surface, or if it's polymer solution, the water has to come from rivers, or have to come from sea, or have to come from produced under, it has to come from mostly from rivers and seas. So usually it gets cooler than what it is in the reservoir temperature. So especially in offshore where the temperature is very cool. So so we are injecting cold water in the reservoir. And so if we are injecting cold water, then there will be heat exchange between the cold water. It is going to pick up some heat, and the reservoir is going to lose some heat. And this will give me a cool zone around the injector. So that's the idea, that we have a cool zone, and you need this cool zone, and so the viscosity in the cool zone of water is higher, because viscosity of water is higher at lower temperature, right? And away it will be lower, so that sometimes may have an impact if it's polymer or something. So there will be an impact of the viscosity and pressure drop here, this cool zone. And I would not again go into detail. We model different zones here, and so to calculate pressure drops in each zone to get the injection pressure. Now, if these injection pressure drops, the pressure drops could be steady, but sometimes if the diffusivity, pressure diffusivity is small, then we cannot use steady state solution, because there would be a long time until we reach this high pressure drop. It will start slowly, and then the pressure will build up. So we need a transient solution. So here you can see the transient solution, the red figure, slowly the pressure should rise. So I need to use this pressure solution for the reservoir pressure drop rather than a steady pressure drop. So I use that solution, we can even use for different changing rates using superposition in time for the rates, and we can use the solution. But so I use the transient state solution, and then I use the steady state solution once it starts to increase the steady state value. So once it reaches steady state, I use steady state solution. But one thing is, this solution I have for transient is only for single phase flow. I don't have a solution for multi-phase flow, which is in our reservoir. Different fronts are there. So for single phase, I need the average mobility of all of that phase, average compressibility and so forth. So I do that by averaging the mobilities and compressibilities of all the fluids together based on the front locations. So once I know the front locations, I can do some averaging, and that is. And I've compared it with CMG simulations. It's reasonably accurate, so we can use this for simple modeling. And so this is the model for the transient pressure drop for a fractured well, and then so I use that, and then okay, so we are done for all the pressure drop calculations in the reservoir. So we can predict the injection pressure. But what about the pressure at the tip of the fracture, and whether the pressure is enough to propagate the fracture? Now for that, I need to know the minimum stress that I need to, that the pressure has to work against in order to propagate a fracture. So that stress value has to be given from some stress logs or some other estimation, or from general theory. We can get an idea based on the depth and vertical stress gradients. One thing is that initial pressure that I need to have an idea, and then I also, since I'm injecting, the pressures are changing, it's increasing the pressure. So if I increase the pressure, then it will increase the stress. And the other thing is the temperature. Since I'm reducing the temperature, it's going to lower the stress, because these are compressive stresses. So pressure increase is going to make it more compressive, and temperature reduction will make it contracting the reservoir rock, so it will alleviate the stress. So the combined effect may be lower or higher, but typically depend on it can be whatever. So case by case, it will either increase the final sigma h min this value. So these are the equations basically for the details if you want. So pressure drop, if you know, in the reservoir, increase near the fracture, then you can find out the stress, far away stress changing. So similarly for temperature, which is basically linear thermal coefficient, is there of we assume. So some numerical modeling has been done to get these equations. Okay, so finally we got the minimum stress, updated minimum stress as we are injecting the fluids, and then once we have that, the tip pressure that I require, the propagation pressure for the fracture, which is at this place is here, should be at least this sigma h min, plus it should have some additional pressure which reflects the creation of the surface that I'm going to have of the fracture. So every time I will grow, these are the simplest, the first order of approximated models. Then now we can go further. So these assume linear elasticity. The rock is linearly elastic, and it does a thermodynamic energy balance to say that whatever surface. So it says when you create a fracture, you are relaxing. The strain energy releases because you open, and it relieves the stress. But that strain energy should be equal to the energy that has been given to the new surface area. So as you break bonds, you will open a new surface area, two surface areas, and so you use the specific surface area U, and we can derive this, and we will get that if you just equate the two, then the fracture will be self-propagating. If the strain energy release rate is less, then the surface energy that you require, which is the dissipation of energy, then it would not propagate. So basically, if P propagation is less than P minus sigma h min, which is the driver, if that is less than this, then it will not propagate. But anyway, once we get this value, then an estimated value, we know we need to have the pressure, the tip equal to this. So once I know the pressure, the tip equal to this, then I know what the pressure I require at the tip. So we know the tip pressure is equal to the reservoir pressure, far field reservoir pressure, plus the reservoir pressure drop in all the zones, with the transient to steady state, and plus the skin pressure drop around the fracture and the cake. Now, as we are injecting, we are increasing the skin pressure drop. So we are increasing the skin pressure drop. So it will increase the tip pressure, but tip pressure has to be just equal to it won't, because as soon as it becomes more, it will propagate and will try to become equal. So how I have to do it numerically to find a converged fracture length. I increase the fracture length a bit, and then that would cause a reduced pressure drop in the reservoir, because a fractured well with longer fracture will have a lower pressure drop in the reservoir. So these two things should give me should remain constant. Basically, I increase every time something here, I reduce something here by increasing the fracture length. So every time this converges, so based on the numerical scheme, I keep my P tip equal to the propagation. That's how I calculate the fracture length, and that completes the model. And this model has been developed into a software at UT Austin, and which can do all of this. And a workflow which requires for this software to be used would be that I would have to collect the data from the reservoir engineers, the layer data, and whatever water injection from production injection, they would require, and the stress and mechanical data from the rock mechanics, and then we can do the study. So just the data would be, for example, well completions data that is anywhere required, and then injection water data that we would require. In case we don't have the concentration or diameter, we would do a sensitivity by varying, whatever they expect it to be, and then we have different results. And filter cake data. So and then reservoir fluid and rock data, petrophysical data, so all the fluid compressibility, viscosity, density, pressures, and so forth, and relative permeability data, and then layer stress data. Permeability here also is for the layer. Each layer, we can have n number of layers, and each layer can have its own fracture growth and fraction of flow going into those layers. So, and finally, thermal data for the cool zone. So all this put together, I'll show you two case studies just so you get an idea. So this was a case study done on an offshore injector in North Sea. Basically, they had an idea that the water was pretty clean in the sea, and they had the data for this many years, to a couple of years, and then the injection rates were varying significantly. And so they had the BHP blue dots, basically the field data, and then I knew it was good concentration, so I put in 1 ppm and small size particles, and I got a reasonably good match. So that suggests that yes, that's how the fracture is behaving. If I don't use the ppm in this, I would not show you, but the match would not happen. And then also a diagnostic plot I made just to find out first whether there is fractured injection or matrix injection, that is no fractures. And we can see that if it is matrix injection, then you increase the rate, the BHP will linearly increase by Darcy's law. That's how it is. And if it gets fractured, then there is a step change, and usually it becomes flat because the fracture is propagating, holding the pressure constant, more or less, and fractures keep propagating, and injectivity kind of maintains. But the length of the fractures are unknown, but we get an idea that we are getting fractures. So injectivity, we saw the injectivity is matching well. So we got some confidence, and we can say that the fracture lengths that we estimated from the model are reasonably okay. And so we found small because the plugging was less because of less concentration of particles in these wells. And so this is one case study. So the one more thing I did in this was I wanted, they had two layers that they injected into, and initially the layers that they injected had almost equal flow distribution. So they had about 50% flow distribution. After 4 years, when they went and did a production profile, a PLT test, log basically for injection profile, they found that, well, one of the layers is getting a lot of water compared to the other layer. And so we know why this happens, because the one layer is getting more fractured than the other layer. That is the most likely reason. And so I did match, I had to, we did not have very accurate data on stresses. And this thing depends on the stresses of each layer. And so, so I had to find, by history matching the stresses, of what is the profile match happening for the layers rates going into it. So through that, we can back calculate minimum stresses, and that's what I did. And I matched the profile over time of the injection into each layer. So we also do sensitivity by finding the effect of different parameters on fracture length, and find out the critical parameters. So typically water quality, sometimes, even the temperature is critical if thermal fracturing is there. So from there we can make decisions. I'll just show you a few more things. Just the polymer, we have polymer injection models also that we have applied, and we have matched to field. So this is another case study where we had a polymer injection after water injection in a field in Austria. It was also very clean water, 1 ppm or so. But we still see an injectivity decline to almost, start with 7, 8 here after acidizing, and it goes back to 2, 3. So it reduces more than half in less than a year. So that will give you an idea that, no matter how clean you make the water, the injectivity does decline very quickly in a year or so. So I did, this match. From that, I wanted to estimate the fracture length, and what I saw was the fracture lengths are not too much, so we are okay. We can grow the fractures further if we want, and that could also be helpful. That I'll show you. And that was in water flood. This is during the polymer flood. In polymer, because the viscosity of polymer was more, and so we have slightly longer fracture half lengths. Polymer is more complicated, but I would not get into that. But anyway, okay. So some more interesting stuff I can show you. This I did the modeling for some Gulf of Mexico. They have they have reservoirs that are loosely consolidated, so they're not very tight. So sand control can be an issue. So they wanted to pack the injectors before they don't want to intervene later, because a well intervention in offshore is very expensive. So they also needed a high injectivity. So sand control may not be very effective because it will have permeability loss. So they had a frac pack instead, which is like a hydraulic fracture only with proppant. So I modeled for this particular scenario with proppant and all, and I'll show you an animation. So basically the model reflects a channeling within the previous fracture, that once the injection pressure starts to increase, then the minimum stress, and we get channeling, and that's how I was able to model and predict how robust these are. And they're pretty robust because they are already fractured wells, so they can take in a lot of solids inside. So you can see the bottom of pressure rise in these frac packs can go up to thousands of days before they reach to initiate channeling even, and depending on the filtration coefficient. This is for very high filtration coefficient. Typically we may be here somewhere. So okay, I also have done for horizontal. The model can also do for horizontal wells. So for horizontal wells, we can see we can have fracture direction in a horizontal well either transverse to the well or longitudinal, or it can be at an angle, but the model I have is restricted to only a transverse fracture or along the well. Along the well is the best scenario because it will have a best sweep and the best fracturing option for it to grow. And so that's why the pressures are lowest. Lastly, I will show you that how effective the fracs are on the sweep. So how far we can go if we allow the fracture growth. So the idea is this was coupled, the injection well model was coupled to a reservoir simulator, and the fracture lengths were fed to a simulator for a 5-spot pattern. And we can see this is injection well in the center and 4 production wells around. And if there is no fracture, then this is how the sweep would be. And if we allow the fracture to go between the producers, then the sweep will increase, as you can show the color. And the percentage is it just keeps increasing, and like 4 to 5% of increase in the oil recovery will happen. Now, if we allow the fractures to grow towards the producers, still the sweep will increase until the fractures grow up to half or slightly more than half the distance between the injector and producers. So we can basically, so if it is 500 feet away or 1,000 feet away, we can still have 100 or 200 feet of fractures, and that will be better for the sweep. So things can go perpendicular like this and they will sweep better. So the idea is we can have better oil recovery if we allow for fracturing. And so thereby, we recommend allowing fracturing to a controlled way, so we can have higher injectivities. We don't have to treat the water and reduce the cost, and we can have higher oil recovery. So I have done a lot of projects and applied this, and new injectors and old injectors. This is some, you can find some projects that have been applied. So the models have been applied for designing new injectors and so forth. And a lot of fields we have worked, but India field I haven't gotten a chance to work on anything yet. These are all the fields, mostly offshore, because offshore is expensive. So everybody wants to design early on properly, so the intervention cost is reduced. And some are onshore, only a couple of them onshore fields, which are history match, few of them history match and design. And these are the operators that were served. And so the message to take away is that, okay, plugging and fracture growth is for sure that happens. Plugging definitely happens. Even fracture growth in most injectors happen over time. And so a model is there, and a model has been used for history matching. It works reasonably well, and it can be used to optimize the rates, the quality, and the fracture lengths for the best injectivities and improved oil recovery. So for example, I haven't gotten a chance to work with ONGC or oil yet to see if we can improve their optimize their injectivities. But like for example, oil has a lot of wells and reservoirs, and they do inject a lot of water. So there may be scope for improvement. And these are some publications where the model details can be found. These are some of the proceeding publications where the case study data can be found. And there's a website if you want some information or contact. Okay, thank you so much for listening. I hope I finished in time. I had to rush in a bit. I'm open for any discussion or questions if I'm able to answer. Am I still with you all? I hope I'm there.
Yes, sir. Yes, sir. We are listening. Yeah.
Okay, so I'm done for the presentation. So any questions or anything any discussion or anything you would like, I can have for a few minutes if you would like. Okay, so I got a question here. Okay, let me.
Dr. Ajay Suri.
Yeah.
I am Jay Segaran from Petroleum Department. Thank you for the excellent presentation.
Yeah, thank you. Yeah.
Because water injection is must. As soon as when we started producing it, we have to do water injection. So because of water injection only, you can able to maintain the reservoir pressure as well as to improve the production. That there will not be much decline. Because of that thing only, Bombay offshore is producing even after touching 40% recovery. But this is not happening in case of onshore. People are saying it is not economically viable. The reserves are low and other things. And other thing is the permeability reduction always taking place, and always the product injection rate also is coming down because we are using it continuously. We are injecting a large quantity. How to maintain it? Because your simulation model says it's so, but however, in the industry persons always looking for all plots, whether our water injection is going as per the direction, or it is going into going waste, or there is some pressure improvement is there, abnormal pressure is increasing. So these type of things are happening. So can you kindly explain how to maintain the water injection as well as how to maintain the water injection path? Because we are desiring to for injecting for improving pressure in particular platform, whereas it is touching to other places and then water cut is going up.
Okay, so well, this is a very important thing that you have raised. Unfortunately, this model is not this model was not addressing the flow inside the reservoir, which is for which basically the problem you are saying is has will be addressed by a streamlined simulator, which will track because of the heterogeneity. It will track. It will okay. I will tell you the benefits of this model also, but on a global scale, if you want to go, this is for near injection well, about like 1,000 feet or so only. But if you want to contain all the fronts where it is going and how, so for that a streamlined simulator is needed, which is not yet developed in this one. That is one thing. But what it can help with is between the different layers. Sometimes if you're injecting in multiple layers, and we may be sweeping one layer, or we may not be sweeping one layer, like I showed you one case study, because of a fracture growing in one layer and may not be growing in another layer. So that it can track, and that it can tell, oh, you are fracturing one layer more than the other, so you need to be careful because the model is telling you. Or else you will have to do a production log or injection profile to be sure whether it is going into both the layers. But the model can at least tell you, can give you a warning first. But if you want to do it like in a complete reservoir, then a streamlined simulator is needed, and that is unfortunately not coupled with this reservoir yet.
Thank you, sir. Thank you very much. Thank you.
Thank you, sir. Thank you, sir. Thank you for your wonderful presentation. Thank you, sir. This is Nagalakshmi, sir. This is Nagalakshmi, head of the Department of Petroleum Engineering.
Went towards to the students also, I hope. I mean, if they were curious or they got anything and it got them interested in any way, that would be something. Or if they can ask some question that we can address, which is maybe.
Okay, it was indeed a privilege to have Dr. Ajay Suri, who gave us an insightful lecture on well injectivity and fracture growth modeling, which was full of wisdom and loads of information. Thank you for the knowledgeable session, sir. I hope all the participants might have got an idea on this topic. On behalf of SPE Amit Student Chapter, we thank you for joining us. An event of this dimension cannot happen overnight. The wheel starts rolling months in advance. We have been fortunate enough to be backed by a team of very motivated and dedicated. So special thanks to our director, Mr. Jayasegaran, HOD of Petroleum Engineering, Dr. Nagalakshmi, coordinator, Dr. Rajesh Khanna, registrar and vice chancellor, and the office bearers for letting us to carry this event successfully. And last but not least, thanks to students for their patience and participation. In case if anyone has missed the session due to some problem, we will be uploading the session on our YouTube channel at SPE Amit Student Chapter. Thank you. Thank you, Ajay sir.